In this example, we want to evaluate the line integral over c of x to the fourth dx plus xy dy, where c is the boundary of the triangular region with vertices 0, 0, 1, 0, and 0, 1. So I've drawn that region below. So one of the things that we can notice is that this curve c is a simple closed curve, and it can be oriented counterclockwise. So we can give it this orientation if we want to. And what we can notice then is that it encloses our region R. So normally what we would need to do to evaluate this line integral, we could try and check if it's conservative to see if any of our theorems from our previous example hold, but we can already just kind of take a glance at it and see that this is not a conservative vector field because the integral of the m portion dy would be 0. The integral of x to the fourth dy is 0 versus the partial derivative of xy with respect to x is going to be y. So we do not have a conservative vector field here, so we can't use any of our nice theorems from 15.3. So instead, perhaps we can take a look at Green's theorem. Now we could just compute it as a line integral, but the thing that we would need to do, we would notice that we've got this simple curve C, it's a piecewise smooth curve, so we would have to split it up into 3 different portions. We'd really have to compute 3 integrals, doing both the 2 legs of the triangle and the hypotenuse all separately. So instead, let's take a look at the region R that it encloses is a very simple region. So notice like this line here is the curve y equals 1 minus x, right? It's got a -1 slope and a y-intercept of 1. So to describe the region R is very simple. We have y going from a bottom curve of 0 up to that hypotenuse curve. So we've got y goes from 0 to 1 minus x, and then x goes from 0 to 1. So this might be an excellent situation where converting from the line integral to the double integral is probably going to be a simpler integral to compute rather than having to split the line integral into those 3 pieces. So what we're going to end up with here then is we'll have that line integral over c of x to the fourth dx plus xy dy. We're going to instead split this to the double integral over R of, we'll do the partial of n with respect to x minus the partial of m with respect to y. And we're going to do this with respect to area. So I'll put the bounds on in a second, but first let's take a look at what those partials would be. So this is the partial with respect to x of the n term, which is the second one, that's the y piece, so this will be xy, and then minus the partial with respect to y of the m term, which is the first one, so this would be x to the fourth. And so then we're going to do this, the way that we set up our bounds over here was we did dy first, where y went from 0 to 1 minus x, and then we did it dx, where x went from 0 to 1. So then computing those partial derivatives, we'll get this integral. The first partial with respect to x is just going to be y, and then the second partial is actually just 0, so then this is going to be dy dx. And then when we evaluate that y dy, we're going to end up with y squared over 2, which will evaluate from 0 to 1 minus x, and then this is still in the outer integral. So then we'll end up with the integral from 0 to 1. We're going to have 1 minus, so we'll have a 1/2 times 1 minus x quantity squared minus 0 when we plug in 0 dx. So let's simplify the algebra of that real quick. I'll just keep the 1/2 on the outside. Even if we want, actually could just pull it right out of the integral altogether. And then 1 minus x squared is going to be 1 minus 2x plus x squared. dx. So we end up with 1/2 times 1 will go to x. The negative 2x will go to negative x squared because the 2's will cancel out, and then we'll have plus x cubed over 3. And we're evaluating that from 0 to 1. So we're going to end up with 1/2 times the quantity 1 minus 1 plus 1/3. And then that will all be minus plugging in 0, which is just 0. So we do have that 1 minus 1. So we really just have 1/2 times 1/3, which is 1/6. So a fairly simple integral once we converted it over. So again, the main idea with this one was it was easier to interpret this using Green's theorem and to see that rather than compute those 3 separate line integrals, just do one single double integral over area. So go from the line integral of the boundary to the area integral of the region that it encloses. And notice that we did not use our previous theorems in this, and we'll kind of see that a little bit in the future where that's the case. But you could think about what would happen in Green's theorem if this was a conservative vector field.